And we'll forward the audio video file to Dr. Burkhart, and then she can distribute it to you after the session is over. All right. All right, so let's get started. Okay, let's start with the first molecule, PCl3. And in working VSEPR, the most important thing that you need to get right is the Lewis structure. So that's why we're going to go through Lewis structures. If you get the Lewis structure right, it's going to be fairly simple to get everything else after that right as well. Okay, so let's start with PCl3 and draw its Lewis structure. Okay, step one, count all the valence electrons. Well, as you recall, the valence electrons is given by the group number. Phosphorus is in group 5. There's 3 chlorines in the molecule. Chlorine is in group 7. So 3 times 7 is 21. So the total count of valence electrons in the molecule is going to be 26. Okay, now the next step is to choose the center atom. It's the least electronegative atom. And as you recall, electronegativity increases going left to right. So phosphorus will be our center atom. So let's draw phosphorus in the center. Draw a skeletal structure with 1 bond between each center atom and each outer atom. So let's put the 3 chlorines out there. Deduct 2 electrons from the total for each bond formed. So we have 3 bonds formed. 3 times 2 is 6. So after we deduct 6, we have 20 electrons left to place in the molecule. Step 4 says place electron pairs around outer atoms to satisfy octets. Now, as you recall, the way we count electrons in a molecule, the electrons that are involved in a bond are counted both on the outer atom and the center atom. So if we look at this chlorine, for example, right now, it has 2 electrons by virtue of the single bond. So to go to its full octet means we have to add another 6. Okay, so that chlorine has its octet. And every chlorine is the same, so we'll just give each chlorine 6 electrons, and they are now all satisfied. And deduct these from the total. So if we put 6 electrons around each chlorine, there's 3 chlorines, 3 times 6 is 18. We have 2 electrons left over. And step 5 says place remaining electron pairs on the center atom. So those 2 electrons will go right here on the phosphorus. And at that point, we have run out of electrons. It also says count the electrons around the center atom. If 8 are present, the structure is complete. So yes, we have our 8 electrons around the phosphorus by virtue of 2, 4, 6 in the 3 single bonds, 7, 8 from the lone pair. So there is our Lewis structure of PCl3. Okay, so now we got the Lewis structure. Let's move on to the electronic geometry. What do we do for that? First thing we need to do is identify the bonding regions and the lone pairs on the center atom. The bonding regions are those where the center atom is involved with an outer atom in some type of bonding, and we have 3 bonding regions. So we're going to call the bonding regions, we're just going to call it B. So we have 3 bonding regions. Lone pairs on the center atom is going to be 1. So we're just going to call that L. And what we now have is the steric number. That is how many regions of electron density are there around the center atom. And it's going to be the sum of B plus L. So that is 4. Now we're going to get to the electronic group arrangement or electronic structure and molecular shape. And I'm going to flip down to a chart which we used once before in a WebEx, and I know I'm going to be going back and forth here. You might have this in your textbook or from some other resource, but if you recall, what we have here is a steric number 4, and we have 3 bonding regions and 1 lone pair. So for steric number 4, our geometry, electronic geometry, is tetrahedral. Now, our particular molecule is PCl3. It has 3 chlorines and 1 lone pair. So the molecular shape, and again, what's the difference between electronic geometry and molecular shape? The electronic geometry represents the orientation in space where all the electrons are held in the center atom. We have 4 positions where there's electron density, but only 3 of them have atoms associated with it. So the molecular shape is only going to be involving the center atom and the outer atoms, ignoring the lone pairs. So the molecular shape will be trigonal pyramid. So let's go back and fill that in. So the electronic geometry from now on, I'm just going to call it EG, and that is tetrahedral. The molecular shape and from now on, I'll just call that MS, is trigonal pyramid. Okay, so that's the story for PCl3. Next thing we want to talk about is if it's polar or nonpolar. What is polarity? Let's look down here. The polarity of a molecule is a reflection of the distribution of electrons within the molecule. Nonpolar molecules have a symmetrical geometry. Polar molecules have an asymmetric geometry. Okay, so let's go back and look at what this molecule looks like in its geometry. So here we are, we're a trigonal pyramid. We have 3 atoms and 1 lone pair. If we had 4 atoms like this, it would be symmetrical. But the fact that we have 3 atoms and the lone pair, that destroys the symmetry. This molecule is asymmetrical. So this molecule, because of the asymmetric shape, it's going to be polar. Okay, last topic that we're going to cover for everyone is hybridization. I have a little summary of what the hybridization means. When we bring these atoms together, we had 3 chlorine atoms, we had a phosphorus atom. You are familiar with the atomic orbitals, 1s, 2s, 2p, etc. So when we take those atomic orbitals and we put them together to form a molecule, we take those atomic orbitals and we hybridize them. They mix them together to form the molecular orbitals that now contain the electrons. So, this single bond, this single bond, this single bond, and even the lone pair is going to be in a molecular orbital. What we're asking is, what is that hybridization? It's really relatively straightforward. It depends on the steric number. If the steric number is 3, it's sp2. The steric number is 4, it's sp3. Now let's take a minute to talk about that. What that means is it's taking an s orbital and 3 p orbitals. The superscript means just how many orbitals from the atoms did it take to combine. So if when we say S, we don't really say S superscript 1, but that's really what it means. So in steric number 4, we have to have 4 areas where there's going to be electron density. And those areas are going to be provided by the S orbital and 3 of the p orbitals. So the hybridization is just a summary of atomic orbitals that gives the right number of molecular orbitals where we can put all those electrons. So we're just going to follow this chart. So it's sp3. Okay, well that wraps up PCl3, so that one's done. And we're going to walk through the same steps with all the other molecules. Okay, maybe I'll give you a minute, see if anyone has any questions. And if not, we're going to keep plowing ahead, and we'll tackle OF2 in maybe a second. Okay, any questions? Okay, no questions. Okay, so let's keep going, and we'll tackle OF2. All right. OF2. Okay, so let's start again. Count all the valence electrons. Oxygen is in group 6. Fluorine is in group 7. 2 times 7 is 14. 6 and 14 is 20. Draw the skeletal structure. So oxygen is less electronegative than fluorine, so oxygen will go in the center. We'll put each fluorine out there. And when you're drawing these Lewis structures, don't worry about getting the angles and the geometry just right. The Lewis structure is just trying to represent where are the bonds, where are the lone pairs. It's not going to be geometrically accurate. Okay, so we have 2 bonds. Each bond holds 2 electrons. We'll deduct 4 from the total. So we have 16 left to place. Just as we did in the prior example, we're going to put 6 electrons around each of the fluorines to satisfy their octets. 6 and 6 is 12. We have 4 left over. And I want to stress, as you're doing these Lewis structures, you have to be very rigorous about keeping track of the electrons. So if you don't, you might miss these remaining electrons, and they're very important. And as it says here in step 5, place remaining electron pairs on the center atom. So these 4 electrons are going to go in the center atom as 2 lone pairs. Okay. Count the electrons around the center atom. So the oxygen right now has 1, 2, 3, 4 from the 2 bonds, 5, 6, 7, 8 from the 2 lone pairs. So the octet is good. So we can say that is our Lewis structure for OF2. Okay, let's now go on and summarize the bonding and lone pair arrangements. Bonding, we have 2 bonds between the oxygen and the 2 fluorines, so B is going to be 2. The lone pairs on the center atom will be 2. So the steric number is once again 4, just as it was in PCl5, but it got there a different way by virtue of 2 bonds, 2 lone pairs. Now, the electronic geometry, remember the electronic geometry is driven by the steric number. And just as it was in PCl5, PCl3 I should say, when the steric number is 4, the electronic geometry is tetrahedral. So that part is similar. Now the molecular shape, that's going to be different. We have a different arrangement. Hold on just a second. Okay, this is online. Okay, you have to call it. You have to call it. Okay, sorry about that. There's a few students that are coming to this room and they didn't realize it was online. So anyway, okay, molecular shape. It's going to be different. Let's go down to this chart and see what we have. Remember, we have 2 bonding and 2 lone pair. So the situation is going to be right here. We have 2 bonds. So in this case, the red center is going to be the oxygen. The 2 green balls are going to be the fluorines. So we have a bent situation. Be right back. This session is online. Online. So we'll see. Okay, we can help you get it set up. It's online only. Okay, sorry about that. Okay, so it's what we call bent. And while we're at it, I don't want to go back and forth too much and give you eye strain. If we look at this molecule, because of those lone pairs, it's again going to be asymmetrical. If we had atoms in every location, as I said before, it would be symmetrical, but the presence of the lone pairs destroys the symmetry. So this is going to be asymmetrical. Okay, so this molecular shape is bent. It's going to be a polar molecule because of the asymmetry that is caused by the presence of lone pairs, and the hybridization is driven by the steric number, and when the steric number is 4, the hybridization is sp3. All right. So far, both of the molecules we've worked have been steric number 4, and pretty soon we'll break out from there and do something different. All right. Okay, I'm going to keep going. Like I said, shoot questions anytime. So we're done with Of2. Let's do CH4. Okay, CH4. Again, let's refer to our notes here. Make this a little smaller so we can keep track. Count all the valence electrons. Carbon is 4 hydrogens. Okay, how many valence electrons come from hydrogen? Hydrogen only has 1 electron. So it's going to be 4 times 1 is 4. So CH4 methane is an 8 electron molecule. Choose the center atom. Carbon will go in the center. Now it says choose the least electronegative atom, and you might say, well, hydrogen has lower electronegativity than carbon. That's true, but hydrogen can never be the center atom. So that's why it winds up being carbon. We're going to put the 4 hydrogens around. By virtue of the 4 bonds we just formed, we will deduct 8 electrons, 2 times 4, 0 electrons remaining. So we're going to check the center atom to make sure it has 8 electrons, and it does. So there we have it. CH4 is all set, 4 single bonds between carbon and hydrogen. Now let's get into the counting. Bonding groups are going to be 4 because of the 4 CH bonds. Lone pairs on the center atom is 0, so the steric number is 4. So again, we have another 4 example. Electronic geometry, tetrahedral. And the molecular shape is also going to be tetrahedral. One thing to know is any time that the lone pairs on the center atom is 0, the molecular shape and the electronic geometry will be the same. We want to just refer to that little chart. Here we are. That is CH4. And as we said a couple of times, when we have all the atoms, all the outer atoms the same, it's going to be symmetrical. Okay. So this molecule is going to be nonpolar because it's perfectly symmetrical. Hybridization, we've seen this twice before. When steric number is 4, the hybridization is sp3. Okay. All right. So that was pretty simple. So like I said, so far our first 3 examples are all steric number sp3. All right, let's do something a little different. NH4+. So polyatomic ion. How do we handle a polyatomic ion? NH4+. How do we deal with that plus? Well, let's look at our rules. Our rules, or our steps, are going to be exactly the same. But let's look at this section here. For polyatomic ions, add electrons equal to the charge for anions, and for cations, subtract. Okay, what does that mean? So if we start off, nitrogen is got 5, it's group 5. The 4 hydrogens is going to be 4 times 1 is 4, which is 9. But what does the plus mean? The plus means that there's 1 electron missing in that molecule. Now, we're not saying it came from the nitrogen, it came from the hydrogen. We just say somewhere in that molecule it's missing 1. So we're going to deduct 1 from the total. And that was what that little note said. Okay, so now what we're going to see is this molecule is going to start looking an awful lot like CH4, right? We have 8 electrons. So let's just go at it. Put the nitrogen in the center because hydrogen can't be a center atom. We have 4 bonds. Now, the only thing that's different about the Lewis structures is when we have a polyatomic cation or anion, we put brackets around it and we show the charge on the outside. And that's a clue that the number of electrons in there is not just a representation of what the atoms bring. It's going to be a subtracted number in the case of a cation or an added number in the case of an anion. Okay, so at this point, this ammonium cation looks an awful lot like methane. So just for completeness, let's write everything down, but it's basically the same thing now as methane. Tetrahedral electronic geometry, tetrahedral molecular shape, nonpolar because it's a symmetrical molecule, and the hybridization is sp3. All right. So let's keep going. Like I said, so far I haven't had any questions, so I'm really either being very clear or there's not too much uncertainty yet. We're going to get to some more interesting examples in just a minute. All right, so let's go back up to the list. Okay, so what are we going to do next? The next 2, let me just jot them down. SO3, so we're done, now we're done with NH4. SO3 and CH2O, and then O3. Okay, SO3, SO3. All right. Okay, so we're going to start out the same way. Count the valence electrons. Sulfur is in group 6. Oxygen is in group 6. There's 3 of them. So the sum of the 18 and the 6 is going to be 24. Sulfur is below oxygen in the periodic table, and as you recall, electronegativity decreases going down a column, so that means sulfur is the lower electronegative element. So we're going to put the 3 oxygens out there as outer atoms. The 3 bonds represent 6 electrons, so that means we have 18 electrons left. We've seen this a couple of times where we put 6 electrons around an outer atom to satisfy its octet. And when we do that, we have no more electrons. But the question is, are we done? Let's go back. I know we're getting a little out of phase with our rules here. Let's look at our rules. Let's make this a little bigger. So we've placed the electrons around the outer atoms to satisfy their octet. Place remaining electron pairs on the center atom. Well, we don't have any. But that doesn't mean we're done. It says count electrons around the center atom. If 8 are present, the structure is complete. If not, go to step 6. That's exactly what we have. That center atom only has 6 electrons right now. If needed, form a double or triple bond to satisfy the octet. Okay, what does that mean? What do we need to do? What it means is we can pick one lone pair, rotate it in to form a double bond. So I arbitrarily picked that oxygen in the lower right. I could have done either of them. And that gets to the topic of resonance, which we're not going to cover, but it's a straightforward application. Okay, if we look at this right now, what do we have on the sulfur? We have 1, 2, 3, 4 from the 2 single bonds, 5, 6, 7, 8 from the double bond. So we now have a good octet around the sulfur. We still have the octet around the oxygen. Remember, counting the electrons, we have 1, 2, 3, 4 from the 2 lone pairs, 5, 6, 7, 8 from the double bond. So we're good to go. Okay, now let's get into our metrics. Bonding. This is tricky. This is something that students often get wrong. The bonding is just how many atoms are bonded into the center atom. We have 1, 2, 3 bonding situations. Now sometimes students start counting bonds and they might get 4. That's not correct. We're just talking about how many regions is bonding going on. There's 3 regions of bonding. 2 of them happen to be a single bond. 1 of them happens to be a double bond, but they're just 3 regions. Lone pair on the center atom, 0. So our steric number is 3. So that's going to be something different, something new. Okay, so where are we? Let's look at steric number 3. It's sp2 hybridized. We'll get to that in a second. But look at the situation we have here. We have 3 atoms in the molecule with the sulfur in the center and the 3 oxygens out there. So what we have is the electronic geometry is trigonal planar. And remember what we said before. Anytime you have no lone pairs on the center atom, the molecular shape and the electronic geometry is the same. It's going to be trigonal planar. Okay, let's get to the polarity question. Is this molecule polar or not? Okay, let's redraw it over here. And I said we're not going to get into the topic of resonance but I think we need to here because the topic of resonance says that if you have a double bond and single bonds in a molecule, there's actually resonance structures that represent that double bond being in the different locations. In other words, instead of having one double bond and two single bonds, the molecule acts as if it has maybe 1 1/3 bonds between each sulfur and each oxygen. What I'm trying to get at is there is no asymmetry about the bonding. All three of these oxygens are the same. So maybe I should draw it more like this. And what I'm trying to indicate is this molecule is perfectly symmetrical. It's a non-polar molecule. Okay, last thing is hybridization. And as this chart shows, and as we have in our handout, anytime you have a steric number of 3, the hybridization is sp2. All right. Okay, so we did SO3. The next one is CH2O. All right. Okay, let's just start. Carbon is group 4. 2 hydrogens is 2 times 1 is 2. Oxygen is group 6. So altogether, we're going to have 12. Now we have a dilemma here. Which of these atoms is going to be in the center? Is it going to be C or is it going to be O? H is disqualified. We said hydrogen can never be a center atom. If we think about it on the periodic table, in the second row, carbon is to the left, oxygen is to the right. The center atom is going to be the least electronegative. That's going to be carbon. So let's start out. We'll put the hydrogens out there. We'll put the oxygen out there. And we have 3 bonds. 3 bonds accounts for 6 electrons. We have 6 left over. We're going to put those 6 electrons around the oxygen. And at this point, we're out of electrons. Now, I won't go back to the steps, but you may recall from the SO3 example, what we do now is say, how many electrons are on the center atom? How many electrons are on that carbon? Does it have 8? No, it doesn't have 8. It only has 2, 4, 6. So what we did in the SO3 example is just what we're going to do right now. We have to rotate a lone pair from the oxygen in to the center atom, and in that way satisfy the octet on the carbon. So there's our Lewis structure for CH2O. This is actually called formaldehyde. Okay, let's get going on the metrics. B, the bonding regions, is 3, just like in SO3 a minute ago. Lone pair on the center atom is 0, so it's 3. The electronic geometry, trigonal planar, just like in SO3. Molecular shape, even though the atoms are different, again, the molecular shape is going to be the same. Anytime there are no lone pairs on the center atom, the electronic geometry and the molecular shape are the same. So even though formaldehyde looks a lot different than SO3, it has some very similar features in both the electronic geometry and the molecular shape. I think it's easy to see that this molecule is not symmetrical, and by virtue of the oxygen and the hydrogens being different. So it is a polar molecule because it is asymmetrical, and its hybridization is again sp2. That is driven by the steric number. Okay, so we're done with CH2O. All right. Okay, next one. Let's see where we are on our agenda. We're making good progress. So we did SO3. We just did CH2O. So we only have 4 or 5 left. So the next one is O3, which is ozone. What's going on with ozone? O3. Okay, so it looks a little strange. A molecule made up of, do lone pairs increase the steric number? That's a question that just came in. Do lone pairs increase the steric number? And the answer is yes, they do. And however, only lone pairs on the center atom affect the steric number. So the question was, do lone pairs increase the steric number? And the answer is yes, they do, but they have to be on the center atom. Let's go back some of our examples. We haven't had too many yet. I guess so far the only example where we had lone pairs on the center atom is the first two. So if we go back to our PCl3, here we had a lone pair on the center atom, and it increased the steric number. Without that lone pair, it would have been 3. With it, it's 4. Here in the OF2 example, there were 2 lone pairs on the center atom, and that caused the steric number to be 4. Otherwise, it would have been 2 just from the bonding. Okay. All right, so we're back at ozone. Okay, seems odd, but we're just going to follow the rules. So oxygen is in group 6, so 3 times 6 is 18. So that's really all the electrons we have to worry about is 18. Center atom, well, they're all the same, so we'll draw 1 in the center and 2 in the outers. The 2 bonds represent 4 electrons. We have 14 left over. So here we go. We put 6 around the outer atoms. Boom, 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 boom. That is going to be 12. We have 2 left over. So we're going to have another situation where we have to put those remaining electrons on the center atom. And we are now again in a situation, I think this is the 3rd time in the last 3 examples, where the oxygen in the center only has 6 electrons. It's short. So we have to make a double bond with one of the outer atoms. Now we've got to be careful. Let's not forget the lone pair that was there originally. That really matters. So this is ozone. Every atom has 8 electrons. The center atom has 1, 2 from the lone pair, 3, 4, 5, 6 from the double bond, 7, 8 from the single bond. Bonding, remember, bonding is 2. There's 2 regions of bonding going on in this molecule. One happens to be a double bond, one happens to be a single bond, 2 regions. Lone pair, 1. So we are once again in the steric number of 3. So this, I guess, is our 3rd example. Electronic geometry, trigonal planar, but because of the lone pair on the center atom, the molecular shape is different. So let's go to our chart and see what that molecular shape will be. So here we are in steric number 3, and where we have 2 atoms and 1 lone pair, we call that molecule bent. So the molecular shape will be bent. Okay, here's the big question, polarity. is this molecule symmetrical or not? Let's replicate the drawing, and we talked about the resonance situation. So as we look at this more or less geometrically correct representation, is that molecule polar or not? Is it symmetrical? And you might say, well, let me represent this a little differently. There are three regions of electron density. Two of them are forming a bond, and one of them is a lone pair. It doesn't look so good, but anyway. The point is, you might say, well, if I look at the molecule through a plane of symmetry here, it looks symmetrical. But what about a plane of symmetry here? What's on the right side of the molecule is a lone pair orbital, a lone pair of electrons, and what's on the other side is an oxygen. It is not symmetrical. So this one kind of goes against your intuition. This is a polar molecule. And you might say, well, with three oxygen atoms are all the same, it looks really symmetrical. Although the three atoms are the same, the way the electrons are distributed is not symmetrical. So it's polar. And if you don't believe me, go Google it. Go Google, is ozone a polar molecule? And you'll see YouTube videos and other stuff. It's polar. Hybridization, this is easy. Every time we have an steric number 3, the hybridization is sp2. Okay, so that's ozone. Okay, what's next? SCl4. So far, we've been doing a lot of molecules in the steric number 3, steric number 4. So we're maybe going to break out and get into some other steric numbers. Okay, but again, the process is the same. Sulfur has 6 valence electrons. The 4 chlorines brings 4 times 7, which is 28. So that gives us a grand total of 34 electrons to build our structure. We'll start off with the sulfur in the center, and that has lower electronegativity than the chlorines. All right, those 4 bonds represent 8 electrons, so we have 26 left to place. Give each chlorine its 6. Okay, 6 times 4 is 24. We have 2 left over, and as I mentioned, you have to be very explicit about these electrons. You don't want to miss that too. Remember, remaining electrons go on the center atom as a lone pair. So if you miss that, you're going to get the wrong steric number, you're going to get the wrong geometry, you're going to get the wrong polarity, you're going to get the wrong hybridization. So the error really cascades through your answer. Okay, bonding regions. We have 4 bonding regions between the sulfur and the chlorine. Lone pair on the center atom, we have 1. So we have now a new steric number 5. Okay, so let's go to the chart, and then I'll represent this in a drawing. Steric number 5 is my personal favorite. It's called Trigonal Bipyramid, and it has the hybridization DSP2. It's a strange situation because it has 4 bonds and 1 lone pair. So the geometry is called sawhorse. Okay, so, maybe I don't want to draw that. So let's write this down. Electronic geometry is called Trigonal Bipyramid. Where did that name come from? What it really means is we have a triangle in the plane. And we have a north and a south pole. So the sulfur sits in the center. And we have 4 chlorines and a lone pair. There's actually a rule for trigonal bipyramid. Lone pairs go in the plane. Lone pairs on the center atom, I should say, go in the trigonal plane. What I mean by that is we're going to put a lone pair here. The lone pair can never be at the top or at the bottom. It always has to be in the plane. The chlorines are going to be everywhere else. So it's called sawhorse. And that might be a little bit hard to envision, but if you made a molecular model of this using your kit, I think you'd be able to see how this does represent a sawhorse. Okay. What's next? Polarity. This molecule is not symmetrical. If you had chlorines in every position, it would be, but the presence of the lone pair messes that up. So it's a polar molecule, and its hybridization is DSP3. If we go back to the chart I put together, there's a little table there that shows it, DSP3. Again, the sum of the orbitals adds up to the number of positions in the steric number. So we use 1 d orbital, the s orbital, and the 3 p orbitals to come up with 5 molecular orbitals. Okay, so we're now into steric number 5. Okay, next, we only got 3 more examples and then we'll be done. SEF6. Okay, so what do we have going here? Well, we have selenium, which is group 6, so that brings us 6 valence electrons, 6 fluorines, 6 times 7 is 42. So we have 48 total electrons to deal with. So that's a big number. Selenium, of course, will be in the center. And I'm just going to write these fluorines around 4, 5, 6. So we have 6 single bonds initially. 6 times 2 is 12. We deduct those. We have 36 left over. Put 6 electrons around the fluorines. Now at this point we've used up all our electrons, and what we normally do is we ask ourselves how many electrons are on the center atom. And remember, we had some issues before where we didn't have enough and we had to make double bonds. Look at this case in selenium. We have 2, 4, 6, 8, 10, 12. Now we have too many. So how do we deal with a center atom that has more than 8 electrons? Well, I put a little blurb in here, and I know I'm zooming back and forth, probably giving you eye strain, but look at some of the exceptions. Period 3, 4, and higher elements. So that has to do, of course, with the row in the periodic table. Selenium is in row 4. So period 3, 4, 5, 6, etc. can have more than 8 electrons. They can have 10, 12, 14. It's because they have d orbitals. They have more places to put electrons. So we don't have to do anything with that Lewis structure. It's actually good just the way it is. Okay, bonding number 6. From the 6 fluorines bonded into the selenium, lone pairs on the selenium are 0. So our steric number is 6. So this is something different. And let's look at our chart. What do we have for that situation? This is octahedron. So it is a a square plane with, again, a north pole and a south pole. Okay, so the electronic geometry is octahedral. And as we said before, anytime you have a molecule with no lone pairs on the center atom of the molecular shape is the same, so it's going to be an octahedral molecule. This geometry is perfectly symmetrical, so it's going to be nonpolar. And the hybridization, hybrid, is D2sp3. And that's clearly shown in this little table here, D2sp3. I also have it in my little write-up as well. Okay, so now we've explored steric number 3, 4. We did a 5 a minute ago, and we just did 6. And for the purposes of 12, 11, and 12, 12, those are all the steric numbers we're going to work with. So let's move on. Okay, here's one that's a little different. I3 minus. Okay, so it's got 3 iodines. And this is a polyatomic anion. So we're going to remind ourselves, how do we deal with a charge on the molecule? Okay, so the 3 iodines themselves are going to bring 21 electrons to the structure. And just as a reminder, when we're working these molecules, we really need them to be an even number. VSEPR and Lewis structures don't really work well with odd numbers. So if you get an odd number, you might want to check your math. The negative charge on the I3 minus means we have an additional electron in there somewhere. So it's actually going to be a 22 electron system. Okay, let's go and build our structure. We're going to put an iodine in the center. We're going to have other iodines on the outside. So we have 2 bonds, so that's going to be 4 electrons. We have 18 left to place. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have 6 electrons left over. Okay, our rule is that those leftover electrons get put on the center atom. And let's see what we have. We have 8 electrons around the center, right? We have 2, 4, actually we have 10 electrons around the center. 2, 4, 6, 8, 10. But iodine is a 5th row element, so that's okay. So here's our Lewis structure for I3 minus. Again, a polyatomic ion, we put brackets around with the negative charge. Okay, let's get into the bonding and the lone pair. Bonding is 3, lone pair is 2, so that's going to be 5. So we actually are back in our steric number 5 geometry. Okay, we don't need to be doing updates now. Please. Okay, let's keep going. So our electronic geometry is going to be, I'll just call it trigonal bipyramid. What about the molecular shape? Let me redraw that trigonal bipyramid situation. And remember what we said. In trigonal bipyramid, if you have lone pairs on the center atom, we put those in the trigonal plane. So they go here. The other iodines are going to go in the bottom and the top. So the molecular shape, if you think about it, it's linear. How about that? Now you can see, because of the straight line of the three iodines and the fact that the lone pairs are in every position in the plane, this molecule is symmetrical. It's nonpolar. And what we saw before for the steric number of 5, the hybridization is DsP3. Okay, so let me hold there for a second, give you a chance to absorb that. And I think in a moment, we'll work the last example, and then we'll be done. Okay, last example is BF3. All right. Okay, let's get into it. Boron, look on your periodic table. It's way over there in group 3. So it brings 3 electrons. The 3 fluorines bring 3 times 7, 21. So it's a 24 electron system. We'll put boron in the center, put the fluorines out here. That's 6, so we have 18 left over. So we're going to put the electrons out here. Okay, now you might say, we've been here before. We run out of electrons, but the boron only has 6 electrons on the center atom. And your first inclination is to start drawing double bonds. But in the case of boron, that is not the right thing to do. Let's go back, and I'll drag you all the way back to my write-up. Let's talk about exceptions. Group 2 and 3 elements, or center atoms, have less than 8 electrons. Beryllium has 4, and here we are. Boron center atoms have 6 electrons. So we're not going to resort to putting a double bond in the BF3 molecule. The single bonds are going to be okay, just the way they are. So boron center atom. My handwriting is terrible. So the boron center atom is okay with 6 electrons. No double bonds needed. Okay, so it's a pretty simple situation. Our bonding is going to be 3. Our lone pair on the boron is 0, so it's going to be 3. So we've seen this before. The electronic geometry will be trigonal planar. And we have, again, another situation where without a lone pair on the center atom, the molecular shape is the same. Trigonal planar. You can see by virtue of the 3 fluorines being all the same, it makes for a very symmetrical molecule, so it's going to be nonpolar. And the hybridization in every case for steric number 3, the hybridization is sp2. Okay, so there you have it. So we've been all over. We've covered steric number 3, 4, 5, and 6. Can you show us, okay, here's a question. Can you show us how to determine the number of lone pairs again? So the question is to show how to determine the number of lone pairs again. So what I might suggest is let's look at a couple of examples where we had lone pairs in the molecule. And let's look at this one right here. So here we had I3 minus. And it goes through following the electron count. We had 22 electrons in the molecule. 4 of them were due to the single bonds, which means we had 18 left over. When we put the 6 electrons around the 2 iodines, that meant we had 6 left over. We have to put those electrons someplace, and the place where those 6 electrons goes is on the center atom. And when you put those lone pairs on that center atom, whoa, wait, I got this backwards. Holy cow. Someone should have told me I made a mistake. The steric number is correct at 5, but there was actually only 2 bonding situations and 3 lone pairs. Maybe that's where that question came from, because I actually made an error there. There are 3 lone pairs in that example. Okay, let's go back to an earlier example, which was right the first time. Here we had ozone. We had a situation there. We had 18 electrons in the molecule. 4 were deducted for the 2 single bonds, giving us 14. 6 were deducted for these electrons to fill the octets on the outer oxygens, which meant we had 2 left over. So the 2 leftover electrons had to go somewhere, and where they go is to the center atom. So that is why we have the lone pair of 1. Okay. I think we had 2 other examples. Let's walk through those. Not that one, not that one. This one's good, the Of2 example. Let's really zoom in on this one. So we did this early, so let's just go back through it. 20 electrons in the whole molecule. We had 2 single bonds, which account for 4. That meant we had 16 left over. We put 6 electrons around each fluorine. 6 and 6 is 12. That meant we had 4 left over. Those 4 electrons went onto the center atom as 2 lone pairs. I didn't do the final subtraction. So that's how lone pairs wind up on the center atom. It comes because as you do the counting and the subtractions, you wind up with a non-zero number, and you have to place those on the center atom. Actually, the very first molecule we worked today, PCl3, was another example. 26 electrons in the whole molecule. We had 3 single bonds. That's the 6. It means we had 20. When we place the 6 electrons around the outer chlorines, that's 18, which meant we had 2 left over. Those leftovers go to the phosphorus center atom, and only then are they deducted and we wind up with 0. So the lone pair, the L here, refers only to the lone pairs on the center atom. We have a lot of lone pairs on outer atoms. They don't count. Okay, only the lone pairs on the center atom is what counts towards contributing to the steric number. Does that help? I hope. If we look at the structure, and actually this write-up that I put together, I will forward that separately to Dr. Burkhart. Maybe that would be useful. Because what we're talking about here is steps 4 and 5. Place electron pairs around the outer atoms to satisfy octets. And then here we go. Place remaining electron pairs around the center atom. Count electrons around the center atom. Okay, here's a great question. The question is, in the I3- example, why can't we make 2 of these lone pairs double bonds? Okay, let's go back to I3. And I'm really glad you asked that question, because when I teach 1211, I see students doing this. And okay, so here's the I3-. Okay, instructors are not supposed to show you how to do things wrong, but let me show you what I sometimes see. Let me just draw this again. Whoop. No, that's not right. There's 3. So let me see if I understand your question. What I sometimes see is students do this. And this is wrong. Wrong, wrong, wrong. Okay, why is it wrong? First of all, let's look at what just happened on this iodine. It has 2, 4, 6, 8, 10 electrons. Outer atoms can never have more than 8 electrons. So when we talk about row 3, row 4, row 5 elements can have more than 8, that's only when they are a center atom. All outer atoms must have 8 and only 8. So these have 10 electrons. So I guess what I'd like to say is in forming double or triple bonds, formed by taking lone pair electrons from the outer atoms this is a great question. I'm so glad you asked. To the center atom. We never form double bonds by taking lone pairs off the center atom and rotating it out. And why is that? Because look at what just happened. In this structure with the 3 lone pairs on the center atom, the outer atoms already had 8 electrons. If we make a double bond, the 8 electrons are already there, and then we're adding to it a 9th and a 10th. And this is no good. Outer atoms, 8 electrons always, and never more than 8. So yeah, I've seen that many times, and unfortunately I have to mark the paper just like I did here. So lone pairs that wind up on the center atom, stay there. Too many electrons on each, you can only have 8 for each. Yes, yes. So outer atoms can have only 8. So if you look at these examples, what we see, so we made double bonds a few times. Let's go back and reflect on how we made those. So we didn't do that at the beginning. Okay, here's the first time where we made a double bond. Okay, what is the situation that causes us to make a double bond? First of all, it's because the center atom is short. It's because the center atom only has 6 electrons. So we have to fill it up. If the center atom has 8 or in the case of iodine where it has 10, 12, 14, it's fine. So the only time you form a double bond is when the center atom is short and you have to bring electrons from the outer in. So in SO3 we did that because we had to. I know some students love double and triple bonds and they draw them all over the place. It's only a measure of last resort. Here in the CH2O example, carbon only had 6 electrons. It was short. We had to bring a lone pair in to form the double bond. Going up here. Look at this Of2 example. When the center atom has 8 electrons, it's good to go. Here in the PCl3 example, the center atom had 8 electrons. It was good. We could have started drawing double bonds all over the place, but we didn't need to because it already had its 8 electron quota. Where else did we draw a double bond? In the ozone molecule. Here we had 8 electrons on the outer atom, but the center oxygen came up short with only 6. So we had to bring electrons to its rescue from the outside in. Now you might say, well, why didn't we do a double bond there? Well, what would happen? Let's redraw this. It's going to be the same problem. Right now, the outer atoms are perfectly good. They have 8 electrons each, right? But the center atom is short. So we have to bring it in. Now you might say, well, why don't we solve that problem by making a double bond with that lone pair? Okay, let's do it. Let's bring this one here. And let's see what we accomplished. How many electrons are on the center atom now? There's still only 6. So we still have a problem on the center atom. And look at what we did over here. We messed up this outer atom. This outer atom now has 2, 4, 6, 8, 10. So I think the takeaway message is lone pair electrons that go on the center atom stay there. They never get involved in multiple bonds. Multiple bonding occurs when the center atom is short on electrons and we have to bring electrons from the outer atom in to solve the problem. Okay, so I went a little bit on a rant there, but I'm really glad you brought that up because I've seen that sort of thing on homework papers and on tests, and I'm glad you brought that up. Okay, anything else? So we're about 1:16, so we've been going a little bit more than an hour, and I think that's really been good. This is an example where questions really make the discussion a lot better. Just lecturing, a lot of times I can't really gauge what's on your mind, so questions really make this a lot better. Okay, well, thank you for coming. Before I sign off, any last questions? Questions we got were really good. Thank you. All right. Well, thanks for coming. I hope this was helpful, and good luck on your remaining tests and final exam. All right, great. Thank you for coming, everyone. All right. So.